Hello viewers, today's topic is about chaotic systems. And before I move towards this topic, I would suggest if you have not subscribed my channel, please subscribe so that you can get in-time notifications about further video uploads about the simulations of different physical systems. Okay, thank you. Chaotic systems. First of all, I come to the word chaos. Okay, so chaos can be defined as a situation of unpredictability, a situation of unpredictability. Okay, so a situation of unpredictability is called as chaos. Okay, so now I come to, let's say, the chaotic system definition. Chaotic system. Chaotic system. A system which shows unpredictable behavior. A system which shows unpredictable behavior. Okay, so that system is called as a chaotic system. So now I come to the, you can say, uh, reasons behind, you can say, the unpredictability behavior of system. So the next thing is about the reasons behind the chaos. Okay, this is my experience, so I'm talking about the reasons about reasons of, you can say, of chaos of a system. So I would say the reasons behind uh, chaos of a system is actually a special, you can say, combination or special interplay among different parameters involved in the system. Okay, special interplay special interplay among you can say different parameters. parameters of a system. Okay, so if a system, you can say, uh, is a chaotic system, so that the system can, you can say, show unpredictable behavior. If we have certain special, you can say, combination of values of different parameters involved in a system. Okay, for example, let's say in case of simple pendulum, uh, if we write it, so let's say a differential equation of a simple pendulum, nonlinear simple pendulum, that is d2 theta by dt2 is equal to minus t over L sine theta, and minus q d theta by dt, and plus fd sine of omega dt, right? So this is, you can say, uh, a differential equation of a nonlinear simple pendulum. Here, Q is, you can say, the damping factor, right? And FD is the amplitude of driving force. Amplitude of driving force. And over here, this omega d is the driving frequency, the frequency of the driving force. Okay, and this differential equation I have written, this is actually the differential equation of a nonlinear damped driven simple pendulum, okay, realistic pendulum. And this type of pendulum has the, you can say, capability to demonstrate chaos, means it is a simple non-linear damped and driven pendulum can show unpredictable behavior. Okay, here you can say the parameters of this system are, the are parameters of this parameters are the damping factor, the driving force, amplitude, and the frequency of the driving force. Okay, so these are the parameters, and special combination of values of these parameters will make this system to behave chaotically. Okay, and in order to have um, uh, a look at, you can say, at the chaotic behavior of this simple pendulum, we can move towards this, you can say, simulation. Okay, keep in mind here, I'm just providing a very brief about chaos of any system. In any other lecture, I will be, you can say, going into details of the chaos or the chaos theory. Okay, so let's go to, you can say, the simulation of the chaotic behavior of a simple pendulum. Okay, let's go there. So I can start here. Okay, this is the you can say interface you can see, and there are you can say three input boxes available here. Okay, the input box for the damping factor, the input box for the driving force amplitude, and the third one is the input box for the driving frequency. Okay, so the parameters of this system are available here, and we can opt certain values for these parameters in order to have, you can say, uh, chaotic aspects of the simple pendulum, chaotic aspects of the behavior of the simple pendulum. Let's choose, let's say, the first combination of these parameters. They are, let's say, 0.5, and let's say the driving force amplitude is chosen to be, let's say, 1.2, and the driving frequency is, let's say, 0.667. Okay, so these are, you can say, this is a spatial combination of the values of these parameters, and there might be many other possible combinations of the parameters of the simple pendulum. So these, you can say, parameters will be effective in case of which we choose here the realistic case. So let's choose the realistic case and I start here. You can see here that the pendulum will be showing unpredictable behavior, and this unpredictable behavior is also, you can say, visible through its oscillations of the pendulum, and also this unpredictable behavior is visible, you can say, in the graphs of theta versus time, and you can say omega versus time, omega versus theta. Okay, you can see here this this yellowish one is the graph between omega means the angular frequency of the simple pendulum, and theta, that is the angular displacement of this oscillating simple pendulum. And this one in blue color, the graph is in between and the changing values of angular displacement of simple pendulum with the best of time. Okay, so if we slightly, let's say, change these, so you can say, values of the parameters. In that case, let's say I use here the value is, let's say, 6. So I have changed these the value of the damping factor slightly. Then we again start, okay, the simulation. Okay, so you can get the graph. Okay, you can see here that by changing the value of the damping factor slightly, uh, the chaotic behavior of this simple pendulum has disappeared. Okay, this means the system, the simple pendulum system, is you can say very sensitive to you can say the values of the parameters. If we change the values of the parameters, very you can say in very small amount. So in that case, the behavior of the system is changed. Okay, so if we let it, we take you can say the damping factor to be same, let's say 0.5, and we slightly, you can say, take a different driving force amplitude. So in that case, we can see here a different type of behavior of the system. Okay, so look at. Okay, so you can see here when the damping factor is fixed, when let's say that is taken to be 0.5, but the driving force amplitude is slightly changed from 1.2 to 1.3. The behavior of this pendulum is very interesting, and means it shows another behavior. And you can say this is not a chaotic browser. Its motion is being repeated again and again. This is very interesting. Okay, so instead of, let's say, changing the values of the damping factor and the driving force amplitude, let's say we are taking the same values, but we are changing here the driving frequency slightly. Let's say we take 0.7. In that case, so we can get another behavior of the simple pendulum. Okay, you can see here. So if the value of the driving frequency is changed slightly from 0.6 to 0.7, this pendulum is showing now different type of behavior. Okay, so that means this circuitic system is very sensitive to slight changes of the values of the parameters. Okay, so we can make a general statement about the chaotic systems that the systems are those systems which are very sensitive to, you can say, certain values of the parameters, or you can say the initial conditions. Uh, those you can say systems are called as chaotic systems. Okay, that's all. Thank you. And so do not forget to subscribe my channel so that you can get in time notifications about a further video uploads about the simulation log for different physical systems. Thank you.